Chapter 8, in Section 2, we're going to be looking at properties of power series. In Section 1, we were looking at polynomials, specifically Taylor polynomials. If we have a polynomial with a certain order n, that's great, it's a polynomial. But as we take the limit as n approaches infinity, we end up with a series, which is what we spent Chapter 7 looking at. Now in this section, we're not going to be looking so much at Taylor series. We're just going to be looking at power series in general, where Taylor series is one type of power series. In section 3, we will specifically look at Taylor series and focus on those. So in this section, we're just going to look at power series. We're going to get some rules. We're going to see how we can work with these infinite term polynomials that we're using to represent functions. So, first of all, what is a power series? A power series, kind of as we saw last section, is the sum of a whole bunch of terms. In this case, a series is an infinite sum of terms. Now, each of these is going to have a number times x minus a to the k, or a lot of times we'll be looking at just x to the k, where it'll be centered around 0, kind of like in the last section. But in general, x minus a to the k. If we expand this out, we get c naught plus c1 x minus a plus c2 x minus a squared plus c to 3x minus a cubed plus etc, etc, etc. Now this looks similar from our Taylor polynomials, and the difference, other than the infinite addition, the difference between a power series and the Taylor series, Taylor polynomials, is simply how we get this constant in front. For the Taylor series, that's where we had the derivative, like the nth derivative over n factorial. That's not the only way of doing it. So, for example, we could have a geometric series. We saw a geometric series last chapter. We have something times a number to the n, where it converges as long as that number, that r term, was less than 1, absolute value less than 1. So if we simplify it down, we're going to take away the constant. So we're just going to have a series of a number that's less than 1 to the n. So say 1/2. That would be 1 plus 1/2 plus 1/2 squared, which is 1/4, plus 1/8 plus 1/16 plus etc, etc, etc. That is a geometric series. We can replace the n with or the r with an x to get something closer to a function. So the geometric series, we're looking at k equals 0 to infinity of x to the k. So we get x to the 0 plus x to the first plus x squared plus x cubed plus x to the fourth plus dot 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 dot. And then if we remember the sum from last chapter, the sum of a geometric series is a over 1 minus r, but in this case a is 1, so it's just 1 over 1 minus r, or 1 over 1 minus x, as long as the absolute value of x is less than 1. We're going to be using this series a lot, going both from a series to a sum to an equation, because this is f of x equals 1 over 1 minus x. We're going to be going that way. We'll also be going the other direction. If we have an equation, how can we write that as a series? And so why would we do that? Why would we write all these series? I know that way back in the day, we used it because we didn't have calculators. And a lot of times what we were doing is how we found those values that we just use a calculator for now. So, I mean, there's some nostalgia there. There's some historical significance there. There's some just underlying what are we doing here issues. But there's also a lot of functions that we really can't write as a function, at least not anything that's going to be remotely pleasant. An example of that is the Bessel function. And this is an example. This is not one that we're going to be using a lot today, just before it freaks you out too much. Just an example of the Bessel function. Writing it as a f of x equals something is not something that we're going to do. However, as a power series, it's not that unpleasant. But here we have our constant term and how that gets found. And then we have our x to the power term. I mean, there's a lot of Bessel functions. It's a whole series of functions. This is just one of them. Um, and I keep calling them functions. How do we know that it's a function? We don't, I mean, how does this even look like? Well, a power series, being that it ends up being a polynomial, it will be a function, which means that each x value will go to exactly one y value. And it'll get closer and closer to what it looks like the more terms we use. Obviously, we can't graph an infinite number of terms. So I went onto my computer and I graphed it up to 500 terms. And it calculated, it timed out after 20 minutes or so. So I scaled it back a bit. I went to 50 terms. And at 50 terms, it took over 10 minutes. I stopped counting at some point, went to another thing. When I came back, it was graphed, but it looks kind of like this. Now I cut it off at about x equals -2 and x equals 2 because that's the only space this function is defined for. If we look, that's in the next slide, that's called the interval of convergence, is from -2 to 2. And so after that, it just shoots up to infinity pretty quickly. And then this is not -1, this is actually -0.25. And so it's going from there. It looks kind of like a normal curve, just shifted down below the axis. But it doesn't look all that strange. But when you look at the equation, it is pretty weird. And this isn't just some random thing. I mean, it is kind of random. But this actually has a lot of applications when you start looking at wave patterns on circular geometries, which would be things like a drum head. A circular drum head, when you hit the drum, sound is made from waves which are vibrating from probably towards the center of the drum head. That's a lot of times where you hit it, but drummers know that if you hit it closer to the edge, you get different sounds. The waves determine the sounds. And on a circular drum head, they're going to behave a lot differently than they will if you're just talking about like an infinite plane. So yes, this does have some value, some significance. It's a fairly specified type of function though. Chances are, unless you're really getting into that stuff, you may never have to deal with this type of function. But if that's what you want to do in life, or perhaps something else is going to come around where you're looking at something circular with wave patterns, a Bessel function might come up for you, at which point series are going to definitely be your friend. And you'll have a lot more tools to deal with them at that point too. So the convergence of a power series. Where does a power series converge? Well, now before we get too far into where it converges, let's look at some vocab. If we have a power series, we have this number in front we already talked about. That's called the coefficient. And then we have this number here, this a value, which we've seen, that's called the center. And then two more things that don't show up right away in the equation, but things that we talk about is the interval of convergence. That's all the x's where the series converges. And we talked about converging and diverging last chapter. That's going to come back right here. And then related to that is the radius of convergence, which is the distance from the center to the boundary of the interval of convergence. So for example, let's say we had a function that was centered at 3. And using what we're going to be doing, we found that, hey, this is going to converge anywhere from 1 to 5. So the interval of convergence would be from 1 to 5, possibly including 1 and or 5, possibly not including 1 and or 5. We'll see that in a second. And then the radius would equal 2 because that distance is 2. And that does not matter if it's including 1 or 5 or not. And so, how can we find these things? So to be finding these intervals of convergence, we're going to be using a lot of the same stuff we were doing last chapter, specifically the ratio test and the root test, which should be somewhat nice to hear. So a function like this, we have a series x to the k over k factorial. This looks like a great one for the ratio test. So that's what we're going to use. The ratio test says the limit as n goes to infinity of, we have x to the n plus 1 over n plus 1 factorial over x to the n over n factorial. We're going to figure out what that is. If that's less than 1, it converges. If it's bigger than 1, it diverges. And if it equals 1, then that doesn't tell us much of anything about that. So, first thing I would do is simplify our numbers. X to the n plus 1, that's x to the n times x. To the 1, we add the exponents, x to the n plus 1, over the factorial. That's going to be n plus 1 times n factorial. We can flip the denominator and multiply. So we get n factorial over x to the n. We can cancel what we have in common, n factorials, x to the n's. So that leaves us with x over n plus 1, and the limit as n goes to infinity. Notice the limit is n goes to infinity. X is not a part of that limit, so we can take it out of the limit. We can move it out to the front. So we have x times the limit as n goes to infinity over 1 over n plus 1. What does the limit as n go to infinity of 1 over n plus 1 do? That goes to 0, so we end up with essentially x times 0, which equals 0. That means that the limit is less than 1, which means that this converges. And not only does it converge, it doesn't matter what x equals. So that means it converges for all x. Well, real numbers that are x. We couldn't possibly have x as infinity or anything, but that does mean the interval of convergence, that's a C, is negative infinity to infinity, and the radius of convergence is infinite. It just means it works for all x. So that's exciting. But what about when it doesn't just go to 0 like that? That's kind of a cheap one. Well, let's take a look at another one. So we have the sum of 0 to infinity of negative 1 to the k times x minus 2 to the k over 4 to the k. This looks like a good one to use the root test for, being that we have a whole bunch of stuff to the k. So we're going to find the limit as x or n goes to infinity of the nth root of, we're going to use the absolute value here. We should have used the absolute value in the last one, but it was going to 0 anyway. It didn't actually matter. But we use the absolute value because the ratio test and the root test only work for positive values. And our sequence could be positive, could be negative, we don't know. So we're always going to use the absolute value here, which means that this -1 to the k isn't really going to make much of a difference at all. X minus 2 to the k over 4 to the k, well, n's, I was just copying the equation above, but I changed the value to n. So when we take the nth root, that's going to get rid of all of the exponents in addition to that -1, leaving us with the limit is n goes to infinity of the absolute value of x minus 2 over 4. Well, all of the n's went away, so that's just going to be x minus 2 over 4, and this x minus 2 over 4 is going to have to be less than 1 in order for it to converge. We can multiply the 4 over to get absolute value of x minus 2 is less than 4, which absolute values you can split up. This means x minus 2 is less than 4, or x minus 2 is greater than -4. Add 2, x is less than 6. Add 2, x is greater than -2, which means we have the interval from -2 to 6. That doesn't tell us about the endpoints. For the endpoints, that would be when it equals 1. The root test doesn't do us any good there. So what we need to do is we need to plug in what happens when x equals 1. Or not 1. What happens when x equals -2? What happens when x equals 6? That's what we need to plug in. So we look at those individually. So we're going to go back up to the original equation. We're going to have the sum from k equals 0 to infinity of -1 to the k times, if we plug in -2, we're going to have -2 minus 2 is -4 to the k over 4 to the k. Well, -4 to the k over 4 to the k is going to either equal 1 or -1. It's going to multiply by -1, so when k is odd, it'll equal -1, and that one will equal -1, so it'll be +1. When k is even, it'll equal positive, and this one will also equal positive, so it'll be +1. So regardless of whether k is odd or even, notice that all the variables disappeared. This is just going to be the sum of k equals 0 to infinity of 1, which diverges, because it'll be 1 plus 1 plus 1 plus 1 plus 1. It's just going to keep getting bigger. So this diverges. And then we can plug in 6. K equals 0 to infinity of -1 to the n. We plug in 6. 6 minus 2 is 4. So we have 4 to the k over 4 to the k. That cancels. So we're going to have -1 to the n, which is going to go -1, +1, -1, +1, -1, +1, which also diverges. So in this case, neither endpoint will converge, which means our interval of convergence is this -2, 6 interval, and the radius of convergence is going to be half of that. So 6 minus -2 is 8, divided by 2 is 4. Also, we're starting out at 2. 2 to 6 is 4. -2 to 2 is 4. Radius of convergence is 4. And that, again, would not have changed if it had converged at one of the endpoints. or both of the endpoints, the radius would still be 4. That the endpoint behavior does not make a difference on that. All right, let's look at another one. We have k factorial times x to the k. Let's use the ratio test again for this one because we have factorials. The root test doesn't work so great with factorials. So let's go the limit as n goes to infinity of n plus 1 factorial times x to the n plus 1 over n factorial x to the n. We can simplify or expand, I suppose. N factorial is going to be n plus 1 times n factorial. X to the n plus 1 is x to the n times x over n factorial times x to the n. We can cancel, leaving us with the limit. The x can go out in front again. We have x times the limit as n goes to infinity of n plus 1, which diverges. So we have x times something that diverges, which is not less than 1. So this will diverge, except possibly, how could we make this less than 1? If the limit is greater than 1, if we multiply by 0, it will be less than 1. So if x equals 0, over on the last one, if this had happened, it would be x minus 2 equals 0. So it's when x equals a, when x is at the center, it can still converge. Because here, if x is 0, it's just the whole thing goes to 0. So it will converge at converge 1. So the interval of convergence is the set of x such that x equals 0. That's just a fancy way of saying it converges at 0. And then the radius of convergence equals 0 in this case. In fact, that'll happen every case when it happens where it diverges. It will converge at the center, the radius will equal 0. So these are the three things that could happen. We could have it converges everywhere, like that first example. We could have it converges on a region, like the second example, or it only converges at that one point that is the center, like the third example. So that's how to test for convergence. If we move on to combining power series. Combining power series can be great when we want to be writing power series because we have a couple that we know, we can add to that. So first, we want to suppose we have two power series. We have a c to the k, x to the k, and then a d to the k, x to the k. They converge to f of x and g of x. So the c to the k one is going to equal f of x, whatever that is. The d to the k is going to equal g of x. So if those two things happen, then sum and difference. We can add them. It's just going to be adding the two or subtracting. So notice it's a plus or minus. When we add, it adds. When we subtract, it subtracts. So we have two converging. Let's say we have the geometric series and then another geometric series. They can add together to be two of the geometric series. It works out the same. Multiplication by a power. So let's say that m is an integer, so that m plus k is going to be bigger than 0 for all terms of the power series, which most likely means that m is going to be positive. However, sometimes we start k at 5, which means m could be one of those beginning negative numbers as well. It will still converge. It'll just be x to the m times f of x. So if we multiply, and we'll see an example of this right away. In fact, I think it might be the first example. But if we multiply x to the m times a power series, then it's going to be the same as x to the m times the equation that would get us that power series, because the power series is going to have x to the k, so it distributes quite nicely. And then composition, if we have a composite function, a function of a function, so we replace a value with a different value, it will still converge as long as the composition is inside the interval of convergence. So let's look at a couple examples of these. If we start with the geometric series, which a lot of times that's what we're going to start with. It's a very simple, and yet it's a very basic power series. I mean, it's the power series which has 1 as all the coefficients. That's the geometric series. So that's a good building block to start from. And we have the equation that it equals too, which is handy. So we want to find x to the fifth times, or x to the fifth over 1 minus x, which we could write as x to the fifth times 1 over 1 minus x, which 1 over 1 minus x we can expand out in the geometric series. This is going to be x to the fifth times 1 plus x squared plus x cubed plus dot dot dot. Distribute the x to the fifth. X to the fifth plus x to the sixth plus x to the seventh plus x to the eighth plus dot dot dot, which will turn into a series k equals 0 to infinity of x to the k plus 5. That's all it is. And that goes with that multiplication by a power. We start out with x to the fifth times the function. Well, that's going to give us x to the fifth times the series of that function, which we could move it into. So that's all that says. We can use some more. So starting again with geometric series, if we have 1 over 1 minus 2 to the x, we could write this out, except that won't be 1 plus x, it'll be 1 plus 2x plus 2x squared plus 2x cubed plus 2x to the fourth plus dot dot dot. And so we just replace the x's with 2x's. This is a composite function, and it's going to have a interval of convergence that is less than what we're dealing with the geometric series, and we'll find that in a second. But so it'll work for all those values. We can take that to the series. So 1 over 1 minus 2x will equal the sum from k equals 0 to infinity of 2x to the k. So we replace the x with 2x here. We replace the x with 2x in the series as well. It happens perfectly. And then also replace the x with 2x when it works. So it's when the absolute value of 2x is less than 1, divide by 2 means the absolute value of x will be less than 1/2, which means that x will be from negative 1/2 to positive 1/2, and the radius of convergence is now 1/2 instead of 1. So we can do it. Do we have to go through all the steps? Could we go straight from the equation to the sum? Depends on what the directions are saying, but yeah, it's very possible. You could probably go from the equation to the sum. Another one, 1 over 1 plus x squared. Same deal, except instead of replacing with 2x, we're going to replace with negative x squared, because this is 1 minus negative x squared. So we'll have 1 plus negative x squared. plus negative x squared plus negative x squared cubed plus dot dot dot. Now, so some of them are going to be negative, 1 minus x squared, but some of them are positive because when you square the negative, we get plus x to the fourth minus x to the sixth. And so it's alternating, but that's okay. We can take that negative x squared and plug it into the summation. 1 over 1 plus x squared will equal the sum from k equals 0 to infinity of negative x squared to the k, which we could simplify. The x squared to the k could be x to the 2k, and that negative can, it'll be just negative 1 to the k. We have to multiply because that'll get us our alternating series. And then we can plug in, so the absolute value of negative x squared has to be less than 1. Well, the negative there makes no difference, so the absolute value of x squared is less than 1, which we square root. X has to be less than 1, which means that we're going from negative 1 to positive 1, and the radius of convergence equals 1. So we know that this is when it works for the geometric series. Whatever we do, we have to do to this guy, and that's when it will work for our composite series. Differentiating and integrating power series. You might be seeing this topic thinking, yes, I've been waiting to do the hardest stuff we've ever been doing with this hardest stuff that we've ever been doing. But honestly, it's really not that hard. I'm going to show you a big box with like the official rules, but remember, a power series is just a polynomial. Integrate and differentiate term by term. All it is, it uses the power rule. And just term by term, you can do it. You can do it to the equation inside the summation, or you do it term by term, and it's not too bad. So if we start out with our power series, it's sum c of k x minus a to the k, and it converges. So we're only looking at that interval. Differentiation, it's differentiable, which also means continuous, on the interval, and the derivative is just found by taking it term by term. Or we go from that, we can multiply the k in front, subtract 1, k times the constant x minus a to the k minus 1. The equation is exactly what we would do if we were doing it term by term. Same thing with integration. We would have to add 1, then divide by the new exponent, plus c. There's that plus c at the end of the infinite sequence that makes a new constant. For all of the x minus a in R. And so this can help us when finding new equations. Example, so we have our geometric series. We're going to find the derivative of this. So the derivative of the 1 over 1 minus x, that's 1 minus x to the negative 1. So the derivative will be negative 1 over 1 minus x to negative 2, or since it's 1 over, we'll square it. So we have 1 over 1 minus x squared. That's going to be, if we did this one, it would just be k times x to the k minus 1, which would equal 0 plus 1 plus 2x plus 3x squared plus dot dot dot. Which this we could actually rewrite if we use these. We could write this as a series to get negative 1 over 1 minus x squared is going to equal the sum from k equals 0 to infinity of k plus 1 times x to the k by adding that, which really just adds 1 to each of those. So there's not much to it. And so that would be if we had this negative 1 over 1 minus x squared that we wanted to write as a power series, or as a power series instead of a function. We could find the derivative of it as well. We know that we have, or not the derivative, the integral. We have 1 over 1 minus x. If we want to find the antiderivative of that, let's use substitution there. That's 1 over u, means we're going to have a natural log of 1 minus x. There's going to be a negative there. The 1 minus x was 1 plus x squared plus x cubed plus dot dot dot. So that's going to end up being x plus 1/2 x squared plus 1/3 x cubed plus 1/4 x to the 4th plus dot dot dot, which we can write as a series. That's going to be negative natural log of 1 minus x is going to be the sum from k equals 1 to infinity of, we have x to the k divided by k, which if we wanted to get rid of that negative, we could make the natural log of 1 minus x is going to equal negative k equals 1 to infinity of x to the k over k. And we could do stuff from here. We could substitute in 1 minus x. If we substitute in 1 minus x, this can be the natural log of x. We substitute 1 minus x in here, we'd have 1 minus x to the k over k. And it keeps going. So with just these few things, we can write power series of a lot of different types of functions. And we could go the other way too. If we started out with something that looks like this, well, let's take the derivative of that. I see if we take the derivative of that, that's going to make those coefficients go away. We're going to get down to something that's like the geometric series, and then we can find the geometric series. So that would allow us to figure out what this one is. There's a bit of playing with it, doing random things with it, and yeah, it's a good time. And it'll get us ready to be working with Taylor series in the next section. So I hope you had fun, but you'll have more fun when you're working on problems. So keep working problems, keep asking questions, and until then, or as always, happy mathing.